Hello, I welcome you all for my concluding lecture on governance. I hope I'll wind it up today. So being the first lecture, a very simple one we chose, and we went really through as if it is a warm-up classes, and went quite slow, and we have taken enough number of classes. I hope you all are convinced about that, and the remaining topics we need to put a head gear, and then we shall cover it at a better pace. The last few terms I want to introduce you. Some of the terms I have already written here. They are controlling force, stability, sensitiveness, isochronism, effort and power. These terms I have already discussed, and I have already solved a couple of numerical problems on this effort and power. Okay. So what are these things? Okay. These are the terms which have been mentioned in the syllabus. That's why. And below I have drawn a line, and another couple of terms I have written here. These terms have not been mentioned in your syllabus, but they used to be there in the previous the syllabus, and sometimes unknowingly an examiner may set the question on this also. That is why I have mentioned, and I shall introduce these terms also. Okay. So from the definition, you are expected to know the definition, and to understand the definition I shall explain and also define. So what exactly you are expected to write in the examination, and therefore, okay, please listen to my explanation and also the definition which I state it later on. So controlling force, the first term I would like to take, controlling force. Okay. So for that, to understand, to make you to understand, I have drawn a diagram here. I hope you all agree that it is a port governor. Upper arms are hinged on the axis, and this is the sleeve. These are the lower arms. These are the governor walls. And let me assume that this governor is rotating at a equilibrium speed. Say at equilibrium speed. I hope you understand what do I mean by equilibrium speed. Equilibrium speed is a constant speed. The speed is not changing. Okay, when the speed is equilibrium, then the sleeve will be occupying at some position. These balls will be revolving at a constant radius. And right now, this is what I can say, that the radius of rotation. So in spite of you have some forces, the weight that is being of the sleeve coming down, the weight of the ball that is happening, and one important force, you have a force in the radially outward direction, which we call it as the centrifugal force, which is equal to mb omega square into r. This is the centrifugal force. So everything, the sleeve is at a constant position, it is not moving up or down because it is an equilibrium position. These walls are revolving at a constant radius of rotation r, and they are also not going outwards, or they are not coming inwards. They are also in equilibrium state. And these walls in the horizontal direction, they are subjected to a centrifugal force. Then in spite of this force, these walls are not moving outwards. That means there must be a force which is acting radially inwards at the wall. At each wall, I must have a force which is acting in the radially inward direction. This force is what is called as controlling force. I hope you understand. Okay. So now coming back to the definition, what is controlling force? Controlling force, as it says, is a force. Controlling force is a force. Okay, where is it acting? It is acting at the wall, at each wall. The controlling force is a force acting at each wall. In what direction? In radially inward direction. Okay, controlling force is a force acting at each wall in the radially inward direction. What is the magnitude of that? If this force is more than centrifugal force, then the walls will come inwards. If this force is less than centrifugal force, then the walls will go outwards. Therefore, these walls are not going outwards or inwards. Therefore, this force, controlling force, also is equal to the centrifugal force. So therefore, now come back to the definition. Controlling force is a force acting at each wall in radially inward direction, having a magnitude equal to the centrifugal force. This force is known as controlling force. I hope you understand. The controlling force is a force acting at each ball in radially inward direction having magnitude equal to the centrifugal force. This is what is meant by controlling force. Okay. So now what is meant by stability? Okay. Stability. What is meant by stability? Okay. So now again come back. So let me. So we have something what is called as equilibrium speed. Equilibrium speed, that is nothing but a speed which is constant speed, and depending upon for that speed the sleeve is occupying a definite position. So every position of a sleeve corresponds to one equilibrium speed. Okay, I repeat it. Every position of the sleeve corresponds to one equilibrium speed. This is true, and the same thing I can tell it indirectly also. So one position of the sleeve, that means one radius of rotation of the balls. Okay, one position, then the radius of rotation of the balls is also constant, and therefore every radius of rotation of the ball corresponds to one equilibrium speed. Okay, so every radius of rotation corresponds to one equilibrium speed. Okay, if this condition, if this is satisfied, then we say that the governor is stable. A governor is stable if every radius of rotation corresponds to a equilibrium speed. Okay, one radius, one speed, different radius, different speed, different radius. So one radius cannot correspond to two speeds, or two speeds cannot correspond to one radius. Okay, one radius, one speed, then we say that governor is stable. A governor is stable, definition. A governor is stable if its radius of, every radius of rotation corresponds to an equilibrium speed. So one radius, one speed, that means the governor is said to be stable. Okay. So what is the meaning, what is the use, etc., application of this, etc. I think that is beyond the discussion. If we are interested, then we can have, so depending upon your interest, then I can discuss more than that. Probably now, from the examination point of view, the definition is sufficient. Stability, this is what is the meaning of stability. So now, let me come to the, what is called as the sensitiveness. Sensitiveness. So while discussing the quarter governor, what is the effect of friction? I have introduced a term what is called as insensitive, coefficient of insensitiveness. Okay, so now let me come back to the governor and okay. So a quarter governor, this is the position of the sleeve. The governor is rotating at a constant speed. The sleeve is in this position. Okay, now suppose the speed changes, say increases, and the sleeve is supposed to go and occupy a new equilibrium position. Okay, whenever the speed changes, the sleeve will change, and accordingly the balls also will move outwards or inwards depending upon whether the speed increases or decreases to the new position. Okay, so if this is happening, whenever there is change in the speed, if there is change in the position of the sleeve, then we say that that governor is sensitive. Okay, a governor is said to be sensitive. So if it changes, if its sleeve changes its position whenever the speed changes. Okay, this is also a term which is used to compare two governors. So I have two governors usually. So every governor, see if it has to work, then it has to be sensitive. Then I want to know which governor is more sensitive. Okay, for that purpose also this term is used. Sensitiveness is a relative term. It is used to compare the performance of two governors. Suppose I have two governors, say 1 and 2. Okay, governor is said to be, a governor among these two is said to be more sensitive if it undergoes larger sleeve movement for the same change in speed. Say I have two governors, say governor 1 and governor 2. So I find out what is delta omega. Say same thing here and here. For the same delta omega in this and this, I find out what is sleeve displacement. Sleeve displacement. See, this is more here and this is less here. Compared to these values only I am writing, this is more than this. Then this governor is said to be more sensitive than this governor. A governor which undergoes, whose sleeve undergoes larger sleeve displacement for the same change in speed, then that governor is said to be more sensitive. So this is another way of talking about what is called as sensitiveness. So apart from this, we have one more. Say I have only one governor. I just want to know what is sensitiveness. How to quantify, how to express the sensitiveness of a governor in terms of some number. Okay, that also is that sensitiveness. Sensitiveness is defined as the ratio of mean speed divided by range of speed. So another definition of sensitiveness is the ratio of mean speed to range of speed. What is mean speed? So let me write down the range of speed first. This is nothing but omega max minus omega minimum. The maximum speed minus minimum speed is the range of speed. And what is mean speed? That is nothing but omega max plus omega minimum divided by 2. And this is what is called as mean speed. So mean speed divided by range of speed is also known as sensitiveness. Okay, this also. And I have seen some books writing this, defining the sensitiveness exactly the reverse way. They write it as range of speed divided by mean speed, and I feel it is not correct, and we shall define the sensitiveness as per this definition. Sensitiveness is this. Okay, so therefore sensitiveness is also over. Then isochronism. Isochronism. What is meant by isochronism? Okay, so a governor is said to be isochronism if its sensitiveness is infinite. A governor having infinite sensitiveness is called as isochronism. Okay, so coming back to the definition here. So when do you have sensitiveness becomes infinity? If omega max minus omega minimum is equal to 0. What is meant by omega max minus omega minimum? That is, omega max is equal to omega minimum. If omega max is equal to omega minimum, then you have only one omega, then omega mean also is omega. That means whether the sleeve is at the lowest position or whether the sleeve is at the topmost position or anywhere in between, whatever may be the sleeve position, you have only one speed. Okay, if the governor's speed is same for all positions of the sleeve, then that situation, that governor is called as isochronism. Okay, isochronism is a governor situation. So when the sensitiveness becomes infinity. Okay, so if the sensitiveness is very high, too much, infinite, then we have this situation. Okay, if sensitivity is too much, then it is said that stability is less. Sensitivity and stability, they are reciprocal to each other. If your sensitivity is very less, then stability is more. If your sensitivity is very high, then stability is very small. Okay, these two go reciprocal to each other. Then this topic, effort and power, we have already discussed it and we have spent sufficient time and we have understood it. That part is already over. Okay, then what is called as hunting and controlling force. Okay, the last two terms which are not mentioned in your syllabus but they were there in the previous case. Okay, so what is hunting? Okay, so consider a governor spindle, only axis I have shown and I have shown only a sleeve. So let me assume that N1 is the equilibrium speed. N1 is shown, the sleeve position. Okay, when the sleeve changes its, when the speed changes to say N2, N2 is more than N1. This is the new equilibrium speed. New speed, new equilibrium speed. Okay, the sleeve is supposed to change its position and occupy what is called as, this is the new position. Okay, this is the new equilibrium position which the sleeve is supposed to occupy. Okay, but what is happening in this hunting? What it knows? So when the speed changes from N1 to N2, okay, this is the final position, final new position. But the sleeve, when it starts moving up, it doesn't stop here and probably it comes up to here. Okay, then it comes to know that I have missed the equilibrium position, then it starts going down and then again it crosses this and probably it comes up to here. Then again it comes to know that it has missed its equilibrium position, then again it goes up, and this is what is going to happen continuously, and this is what is called as hunting of the governor. In hunting of the governor, the sleeve does not come to its new equilibrium position suddenly, and in reaching the new equilibrium position, it moves over and below that position, new position, and this process is called as hunting. Then what is controlling force curve? So as the name says, it is curve. Okay, it is a graph. It is a graph of, okay, graph of two variables, two things. One is what is called as controlling force, taking along the y-axis, and radius of rotation along the x-axis. Okay, if you plot for different radii of rotation, what is the controlling force, and plot a graph, and that graph is called as something like this, and that curve is called as controlling force curve. Okay, unfortunately your syllabus doesn't mention about the discussion of the significance of all that. This is very, very important, controlling force curve. Looking at the controlling force curve of a governor, we will be able to tell how sensitive it is and what is the stable, whether the governor is stable or not. Okay, so with this I feel I have touched all the topics, all the points of the governor, and I wind it up, and maybe in the next class we shall start discussing static force analysis, but the pace will be very, very high, and that means the topic is very simple. I don't have to teach any new topic. I want you to sit along with me, okay, along with that few drawing instruments. The topic what I am going to discuss is a graphical one, so I want you to bring prepare along with the drawing instruments and probably calculator. Okay, thank you.